All right, as I said, this is not a good flow net. And what's wrong with it? Well, first of all, equal potential lines cannot cross each other, and flow lines cannot touch each other or cross each other. If you look closely, well, we know one flow line that's not really shown here is this flow line that goes along there. And what do we see? We see that there's a flow line and it touches there. There's another extreme flow line that goes along here that's not really labeled. And what do we see? This flow line touches here. So flow lines don't touch or cross, and equal potential lines don't touch or cross. And let me show some equal potential lines. In other words, this is an equal potential line. Why is that an equal potential line? Because if I put a piezometer anywhere along here, the water level goes to right there. So as I say, this is an equal potential line. Well, this is an equal potential line also, and they're touching at that location. This is an equal potential line. It's touching at that location. This is an equal potential line for the same reason on this side, and this is an equal potential line. It's touching. This is an equal potential line. It's touching. So there are a lot of mistakes besides bad squares in this particular flow net. So instead, the right flow net for this is this one, and you can see that the equal potential lines always come off the dam like that. They're coming. An equal potential line doesn't come from here; it comes from the dam. In a sense, because here's the flow line. It's got to be perpendicular to the flow line. Here's a flow line. It's perpendicular to the flow line. So. And you can see that so here's a flow line here. We don't show it, but there's a flow line here. There's a flow line here. And there's a flow line here. We have those flow lines, and the way that we look at it is that we count the number of flow pipes or flow paths. So, in other words, what we end up with is you envision the flow going, let's see if I can do this, through here in this flow path. So this is a flow path or flow pipe. That's one of them. And there's, we can do another one here. This is another flow pipe or flow path. Why do I call it a flow pipe? Because it's like water flowing through a pipe. Because there is no water that crosses those flow lines. So it's like that's a pipe, and then our last one is in here. This is our last flow path. So we have 3 flow paths in this, 3 flow pipes, however you want to look at it, in this particular flow net. And in all the flow nets that I give you, pretty much, they're all going to be with 3 flow paths or 3 flow pipes. And, okay, in addition, we count the number, what we're going to call the number of equal potential drops, ND. And for this particular flow net, each flow net is different. What do? I count the number of squares in a path. So I pick this path, and I count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we call this ND, number of drops, which is the number of squares in a path, 11. Now it doesn't matter which path I take, I'm always going to end up with 11. So let's do the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I get 11 for that one. And then if I count the other one, I get, this counts as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it doesn't matter which flow path I look at, I'm going to end up with the same number of squares, so-called squares. Remember, this is obviously not much of a square, but we call it a square. We always end up with the same number. In this particular case, this flow net has 11. Each flow net is going to be different, though. Again, this is the same. Okay, I'm just going to skip that. All right, now this gets a little bit clumsy with a lot of details, but let's look at this flow net and the we're going to solve some problems here. So what we're saying here is this dam is 400 feet perpendicular to the paper, and the permeability of the soil is 10 to the minus 6th feet per second. And we want to our goal will be to find the pore pressure at A, U sub A, pore pressure at point B, U sub B, pore pressure at point C, U sub C. And we want to find the flow Q. We all know Q from your pipe flow fluid mechanics class, which is Q is equal to what? V times A, velocity times cross-sectional area. It's a similar calculation. So I want to know, in other words, what is the cubic feet per second going underneath this dam? Okay, so the flow net is given, and we're looking at a water level on this side and a water level on that side. It's a little bit of a mess, so I apologize for that. But what we're going to do, what we need to do is we need to draw piezometers at each point we're interested in. So in other words, we're interested in points A, B, and C. Point A is given here. Point B is given here. Point C is given here. We have our depths there. So the way to work these problems, and the trickiest part is getting the pore pressure. If we get that, then that's the hardest part. But it's pretty straightforward. At each location, I draw a piezometer. So when I say draw a piezometer, that means that I draw basically a tube going from the point. So I draw a tube at B. I make it go real high, or A, and I do one at B. Make it go real high. So you do your calculations, right? One at C, like that. And my goal is to figure out what is the water level that's going to be in that piezometer. And the flow net is going to help us do that. So in this particular case, we are going to notice that the water level difference from the upstream side of the dam to the downstream side of the dam is 30 feet. That is given information. And the flow net has already been drawn, so let's count how many squares we have in a flow path. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're a little bit lucky we got 10. It's a good number to work with. But that's just by coincidence. They don't all have 10. We just looked at one where it was 11. Now, what does that mean? That means that we are going to compute the drop per square. Well, the total drop is 30 feet. There are 10 squares, so I take 30 feet over 10, and that means the drop is 3 foot per square. So how do we use that in our little piezometers? Well, it's pretty straightforward. If I look at this middle flow path, what do I see? I see to get to point A, I have to go through 2 squares. I go through square 1, that's 1. To get to point A, I go through 2 complete squares. Since I have a 3 foot drop per square, then that means 2 times 3 is 6 feet. That means my piezometer water level is 6 feet below the upstream water level. Let's look at point B. For point B, to get to point B, I go through 1, 2, 3, 4, 5, 6, and then the last one, I have to go through 7 squares to get to point B. Well, since there's 3 foot drop per square, that would be a drop of 21. 7 times 3 is 21 feet. So I look at my piezometer at B, and what do I see? I get a 21 foot drop from the upstream water level. So it's pretty straightforward. Let's do point C now. To get to point C, I'm in this flow path. 1, 2, 3, 4, 5, 6, 7, 8. I'd go through 8 squares to get to point C. So at 3 foot per square, it's 8 times 3 is 24. I get a 24 feet drop from the upstream water level. So I get a drop of 24 feet. Okay, so I now have established the 6 feet, the 21 feet, the 24 feet. Now all I have to do is look at my geometry and figure out what is the vertical distance between each point, for instance, between point C and the water level, between point A and the water level, between point B and the water level in the piezometer. So that is going to give me my pore pressure. So I just have to pay attention to the geometry. I look at point A, and if I look across here, A is at 20 feet. So this is 0, this is 12, and then I go another 30 up to here. So I have to do all of that. But in other words, this whole distance here, by looking at this, is going to be 20 plus 12 plus 30. So 20 plus 12 is 32, plus 30 is 62, and I subtract off 6 feet, so it ends up to be that the distance between the point A, the vertical distance between point A and the water level there is that, and that is 62 minus 6, which is 56 feet. That means my pore pressure is 56 feet times gamma W. That's computed here. Again, for point B, I look at the, I'm looking where point B is. I look at point B, I get 30 feet here. And so again, I go, this vertical distance then will be what? It's going to be the 30 feet plus the 12 feet plus another 30 feet. So 30 plus 30 plus 12 is 72. And the drop is 21. So the distance from B to there is 72 minus 21, And that means my pore pressure is 72 minus 21 times gamma W. That gives me the pore pressure at B. And then I do the same thing for the pore pressure at C. And I look at C. C is at 10 feet. So I have 10 plus 12 plus 30 is 52. And the drop is 24. So 52 minus 24 times gamma W gives me the pore pressure at C. Okay, so I've found my UA, UB, UC. One thing, if I didn't point out, my permeability of that soil, in other words, the permeability of this soil underneath the dam, is 10 to the minus 6 feet per second. Now, some of you did the permeability labs, and you know what that is. Unfortunately, we weren't able to do that lab for everybody, so some of you, all I can tell you is it's a soil property, and it tells us how fast the water moves through the soil. Okay, so without deriving it, I'm just going to give you this expression that for the Q is KH NF over ND times L. What does that mean? It comes from Q is equal to V times A. All right. And it's for the flow now. Units cubic feet per second. So I've asked you to memorize this expression here. What are the meanings? K is the permeability of the soil. In this case, it's 10 to the minus 6 feet per second. H is the total head drop, the 30 feet. In other words, the total head drop is this number from the upstream water level, downstream water level. The difference is 30 feet. That is our H in this particular case. So the total head drop is H. It's 30 feet. We said the number of flow paths is 3. What is the number? Flow paths, I got what, 1, 2, 3 flow paths or flow pipes. Is 3. We counted the number of drops per path was 10. And L is the distance perpendicular to the paper. That was a given information. L is 400. In other words, the dam is 400 feet perpendicular to the paper. So that is a given. So the L is given. I plug everything into this expression. I look at my units. So the K is 10 to the minus 6. H is 30 feet. NF over ND is 3 over 10. And L is 400. And we end up with 0.00360 cubic feet per second. You can check the units, but it comes out to be cubic feet per second. All right, and I want to define one more thing here, and that is the hydraulic gradient. This is a definition. Define the hydraulic gradient for each square. Well, each square is going to have a different hydraulic gradient, and I'll explain why. Because each square is not the same size. As we pointed out, we have squares of lots of different sizes. So in other words, here, in this region I've got a small square. In this region I've got a big square. So they're all squares, but they're squares of different sizes. Now the head drop per square is the same. In this particular case, for instance, we calculated out that the head drop per square was 3 feet. Of course, that's for this problem only. It's going to be different for other problems. But we define the hydraulic gradient as delta H over delta L, where delta L is the width of the square. So since each square has a different width, then each square is going to have a different hydraulic gradient. And what we will note is what? The square with the greatest hydraulic gradient is the smallest square. Why? Because the smallest square because that square has the smallest delta L. Delta L, the width of the square. If it's a small square, it has a small width, we have a big I. We're very much interested in what we call the exit square. What do I mean by the exit square? In other words, if you look at the way the water is flowing here, it's basically flowing upward at the very end. And what can happen is that if the velocity of flow at the end here, especially in this region right here, right next to the dam, that's usually the critical place. If the velocity is very high in that region, then the soil particles can actually be lifted up and floated. And if the particles are floating, then they have no strength. If the soil has no strength, then you can lose your dam because you're going to have your dam with no soil strength supporting it. So we're concerned about the smallest exit square. The smallest exit square, if you look here, so in other words, we can consider, this is an exit square, this is an exit square, and this is an exit square. Well, the smallest exit square is the one, it's usually the one next to the dam. And so if we look, well, so it's hard to say, but if I drew this to scale, that width of that square is about 7 feet. It's not perfect, but I didn't draw that very well to scale. So if I have a delta L of approximately 7 feet, and my delta H, which is the drop per square, is 3 feet, 3 feet over 7 feet, I get an exit gradient of 0.429. That's the hydraulic gradient, so you need to know. Okay, I'll stop.